Log on, tune in, find out. Another good idea from Cambridge.
Well, first I want to thank everybody for being here today and the opportunity to talk to you about some of the things that we've been working on. I'm a bit of a computer experiments newbie, so hopefully I won't say anything too ridiculous. If I do, Derek's back there and he'll knock me around and get me back in line. This is a project that actually started several years ago. I work in the Math Institute at NCAR. The acronym is IMAGE, right? Not image. You have to say IMAGE, or Doug Nitschke gets very mad at you. But it started with one of our Theme of the Year programs, joint with SAMC, and the idea was to try to bring the computer modelers at NCAR together with statisticians to try to do a better job of doing computer modeling completely through the process. And a couple people were involved with that. Jonty worked with some groups on the TIE-GCM model, and we got involved with the LFM model of the magnetosphere, and that's kind of what I want to talk about today. So Mike Wiltberger is a scientist at NCAR who focuses on space weather. This really isn't my talk. This is actually Will Kleiber's talk, who's one of my postdocs right now, who's doing an excellent job on this. Shane Reese and Derek are part of the project, and Matt's around here somewhere too. Matt's worked on this for some time as well. I'm going to talk a little bit about the magnetosphere. It's kind of one of those things that I didn't really know anything about when I got started, but I think it's good to kind of give us some context about what we're trying to do. A little bit about the LFM model, nothing fancy there, the Lyon-Feder-Mobarry model of the magnetosphere, and then talk a little bit about how we're trying to approach calibrating this computer model. Now, what we're really interested in is solar storms and the impact that the solar storms have on the Earth. So here you got a nice representation of the sun. A big coronal mass ejection from the sun. Basically, it's when the sunspots kind of become unstable. They're like knots in the magnetic field of the sun. Is anybody here? Nobody here is into space physics, right? I just want to make sure. Okay, I'm good. I can say whatever I want. Well, the way I understand it is there's knots in the magnetic field of the sun. They kind of become unstable and spit all this stuff out. In fact, a couple weeks ago, there was a really big one, and in some sense, we're kind of lucky because it went the wrong direction. The magnetosphere, and I'm going to show you an animation in a minute because I start talking about the physics of this stuff, or I start listening to Mike talk about the physics of the magnetosphere, and I get a headache. This is really, way beyond that elementary physics class that I had in college and, slept or perhaps drank my way through. Basically, the magnetosphere is this kind of nebulous place in the upper atmosphere that's kind of defined by the interaction of the solar plasma from the sun and the Earth's magnetic field. I say that because it's not really a sphere at all, and it actually moves, okay? It's not constant because of this. It's right at the edge of this interaction. But basically, it's one of the things that allows life to live on this planet, right? If we didn't have the magnetosphere, basically the sun would fry us, okay? So it's basically kind of what's keeping us all together. Then there's all kinds of, now we get into stuff that gives me a headache, right? You start talking about magnetic field lines and all this other stuff, but I'm just quickly here show you a quick picture of what one of these storms look like and what actually happens if I can figure out what happened to it. All right, sometimes YouTube is a great thing. All right, so this is the sun, as I'm pretty sure you can guess. I didn't put this animation together. I don't know who did. I just kind of stole it. So here we see one of these coronal mass ejections coming out from the sun, one of these solar storms. It impacts the Earth, and as you saw right there, the magnetosphere kind of protected it. Most of the energy in the plasma from that thing was pushed off into space. We'll kind of come back a little bit. Yeah, it's pretty short. So we'll watch it again. This is a good animation, right? So here's the mass ejection, the plasma coming towards us. Most of it's pushed off, all right? Some of it comes all the way around, and because of the magnetic field lines, it reconnects behind the Earth. Those ions, that plasma, come in back into the atmosphere at the poles, and the most immediate implication of that is we see the aurora, okay? And so that's the kind of phenomenon we're trying to model with this thing is that interaction between the solar plasma and what happens when it hits the magnetosphere, and then what happens is those electrons and that highly charged energy enters into the atmosphere at the poles. Okay. I can get back to, oops, that's not my talk. All right. So when these things happen, these solar storms can have a lot of impacts, right? The most nebulous thing or the least dangerous of these things are the aurora, right? We get some pretty lights in the sky, right? But beyond that, all kinds of bad things can happen, right? And if you just kind of type in solar storms into Google, you start seeing things like this. Evidently, the Mayans were right, and next year we're all gonna get fried because something's gonna happen. Turns out next year is a kind of a solar maximum, and then there's something right going on with the magnetosphere. Anyway, there's a lot of potential over the next couple of years for some very, very large solar storms. And there's all sorts of things people are talking about. I love this global Katrina. In all seriousness, though, these solar storms can have a lot of very negative impacts. The most immediate one is it interferes with our satellites. Everything from ruining the signals that we get from the satellites to the Earth, so it can have serious problems with GPS. Evidently, there's this system, the Wide Area Augmentation System, which is basically put in place to help airline pilots basically fly their planes. So if everything else goes kaput, they can still contact the WAAS, and they can still actually, we can still actually get around. It can also, beyond just simply messing up the signals from the satellites, it can actually ruin them themselves. Everything from very small things, satellite drift, it can push the satellites off the orbit, or it can actually just simply fry the electronics altogether. I actually read somewhere that half the reason Skylab came down early was because of interference from solar storms. So, and it's actually shut these things down. It's shut down polar routes in particular for airplanes in the past. This is part of the reason why flight crews are really, fancy radiation workers. These things can actually have serious impacts for astronauts. There was a 1989 storm that evidently, if you were standing on the moon in a standard issue spacesuit, you would be dead, right? So this has serious concerns for our astronauts in the space station and beyond. There was a storm in '89 that cut off, now the big thing is power grids, right? We're putting more and more stress on our power grids. There was a storm in 1989 that cut off power in Quebec. There's a National Academy's report running around talking about this global Katrina, okay? If we hit with one of these really big storms, the power grids are already so stressed. You knock out that big power grid, and you can all imagine the kind of chaos that something like that would happen, say over North America or Europe or something like that. It could be a real problem. So one of the most immediate impacts of this research is trying to build a space weather prediction program or model that would actually be kind of an end-to-end computer model, if you will, of this kind of space weather. And this is just one piece of it. Now the LFM model, okay, right? These three guys, Lyon-Feder-Mobarry, all right, are basically, let's see if I get it right this time, the magnetohydrodynamics of the atmosphere, or of the upper atmosphere. Basically, it's simply five basic equations and how we solve these things. The model that we have is run at different resolutions. Now, that doesn't give us a different output grid. It has to do with the resolution at which the MHD plasma is modeled. The single resolution model, on an 8 processor machine runs about near real time. So one run of this to get a 2-hour storm takes about 16 hours of computing time to spin up, run this 2 hours that we really need. The double precision in our experiments takes about 3 days to run a single run. The quad precision, I don't have any idea. Shane Reese, who isn't here right now, won't let us run it on his cluster because it basically shuts down his machine for several days. So we're still trying to get extra computing time on the in-car machines to try to run these things. But one of our goals, one of many goals, is simply, we've heard a little bit about this, is how do we leverage these kind of lower fidelity but cheaper, models against these higher fidelity, very expensive models. So that's one key aspect of what we're trying to do here. Now, the magnetohydrodynamics is actually fairly well understood. What is a problem is then the pieces of the model that take the electrons out of that plasma and bring them down to Earth, so the precipitation model. When Matt was working on this several years ago, we had one model. We're working with something called MIX, and now MIX is obsolete, and there's another one. I mean, these things are not very good, and I'll talk about that in a minute, but the model improvements are being made almost faster than we can actually look at them. They call these empirical equations, and that's what we're after. They're kind of a bit ad hoc. I say that not because, well, the way it was described to me, these are really smart guys, and they're thinking about how this works, and so these equations are motivated by what they understand about the magnetosphere and how electrons precipitate, but it's maybe not quite as rigorous as anybody would want. Okay, so we basically have three parameters right now, right? Alpha, beta, and R. Alpha simply controls how the initial energy of the precipitating electrons is related to basically the thermal speed and the the MHD plasma. Sometimes acronyms are nice. The thermal flux is related to beta, which again relates to the density from the MHD. R tells us something about the potential energy difference between the boundary of, if I get this right, the boundary of the magnetosphere and the ionosphere. And then at the end of the day, what we're interested in is the total energy of the electron precipitation and the flux of the electron precipitation, which are functions of these three unknown parameters, right? Fudge factors. These guys are pretty honest in saying that they don't think this is right, okay, but they think they can twist these three parameters around and get a reasonable picture of what's going on. Okay, I got another cool animation here. So this is what the model looks like. Let's see. All right, so this is an animation of what the model actually does. So what you see here in this kind of these ghostly looking contours is actually the magnetosphere responding to the solar plasma, okay, or the solar wind. And that's what I was saying before. The magnetosphere is not this kind of constant, thing, this constant shield around the Earth. It's moving all the time in response to the energy coming from the sun and the electron, the magnetic field of the Earth and the energy coming from the sun. Okay, so let's see here. Oops. So as this thing moves around, what you see here is actually what we're interested in, and that's the aurora. Okay, so what we're seeing in this piece right here is basically, and I think this is actually the energy of those electrons kind of coming in from the poles, and that's ultimately how we're kind of in an indirect way kind of gauging whether this model's doing the right thing or not. Okay, so and as I said, this is a part of a bigger modeling effort in reality. There's something now, the Center for Integrated Space Weather Modeling. They're trying to come up with predictions, much like you and I listen to the weather and the news in the morning and try to figure out whether it's going to rain tomorrow night. These guys are actually trying to predict whether or not there's going to be a solar storm, and it involves a whole lot of pieces. The LFM is just kind of one piece there in the middle. Some of it is models of the sun and how these solar these CMEs are coming off of the sun, how they interact in the magnetosphere, and then how everything precipitates down into TIE-GCM, which is a model of the upper atmosphere. And eventually, this all gets into a whole nother model called WACM. I love that acronym. That's basically the entire Earth. I mean, from the the troposphere all the way up. Okay, so let's get back to our problem, right? We want to see, basically it's a simple idea. We just simply want to find values of these three parameters that mimic the conditions under a particular solar storm. We get output that's a bivariate spatial temporal field. We're going to get energy and flux from the model. We have observations from remote sensing, the polar UVI instrument on one of the NASA's geosatellites. So in some ways it's a little indirect because it's kind of just taking a picture of the poles, where we get energy and energy flux. So we kind of move everything around to make things match up. And this is a pretty big data set. We have 18 time points in this 2-hour period, Each one of these time points gives us about 170 spatial observations, so kind of one run is about 6,000 correlated observations, a spatial temporal field. All right, so as I said, one of the ideas here was to try to do something to leverage the faster running single resolution models versus the scientifically better but slower running double resolution. So we started off with a very simple idea. We ran 20 single resolutions runs on a space filling design, and then we picked a space filling design of those 20 with 5 of the double resolution. So we have 25 total fields coming out, or runs of this model, and it took about a month of CPU time just to do 25 runs. So this is kind of just give you a picture of what the model output looks like. This is for the exact same parameters, the single and the double. And right off the bat, when we started talking to Mike, Derek might have been, I think he was even there 4 years ago, I think. Mike was kind of complaining about the single resolution runs not being very good because they basically produce fog, not rain. It's kind of a strange thing to think about when you think about electrons coming down, but at the end of the day, what the single resolution gives us is something that's more diffuse and not have those kind of peaks, those kind of, well, you can kind of see it here. You kind of have this kind of diffuse area here, nothing really well defined, whereas the double resolution kind of gives us more well-defined peaks. We'll come back to that in a minute because I think it's going to be very useful in how we link these things together. We might have to think about doing it in a slightly different way. All right, so again, this is a first pass at trying to put all these things together. Well, maybe not a first pass. Matt did the first pass a long time ago. This is maybe the second pass. We have a simple observational model. We're going to kind of assume right off the bat that the double precision model is a lot better and it's kind of a more accurate view of reality. So we simply are going to let our observations look like the double precision model plus some sort of measurement error, and then we'll link the double and the high resolution, or the double resolution to the single resolution plus some sort of delta or deviation or bias term. As I said, these outputs are multivariate spatial temporal field. One of the first problems we had is how do we kind of try to reduce the dimensionality to do something meaningful. We tried to get Mike to tell us a way of just kind of collapsing all this data over space and time in a way that made sense to him, but they really do need a pretty accurate view of these spatial and temporal fields because these things are then fed in, as I said, fed into a whole nother model, and so you kind of need to have a good understanding of how the spatial pattern, if you will, of the electrons and precipitation. If you look at these things long enough, the way they kind of work is during the course of the storm, it almost looks kind of like a bowl, and it kind of goes up and down. It kind of increases in magnitude as the storm progresses and then drops down. And the nature of that kind of bowl moving up and down seem to be pretty heavily related to the parameters. And then the features, the individual features, seem to be kind of like a smaller effect. This kind of suggested to us doing some sort of principal components type dimension reduction idea. And that's basically what we put forth by writing the single, if you will, as some sort of EOF type, geoscience speak, right? EOFs, principal components. Anymore, I just think of them as the same things. Split them off into the principal components spatially, and then let the coefficients kind of end up being functions of time and our parameters, alpha, beta, and r. Now, we do have a lot of information from those equations, those very simple equations to build into our models. So when we look at energy, we look at energy flux. We do kind of have some idea of how these things should behave. And that first principal component, basically in this case, behaves a lot like a mean. And so we've added some structure to those mean functions, at least for the first principal component, that are functions of alpha, beta, and r. And they're simply motivated by those equations and then some very good exploratory analysis that Will has done. We typically use between 3 and 5 principal components, depending on whether we're modeling energy by itself or flux by itself or both simultaneous. The second on up principal components, those have all zero mean because they're basically capturing the perturbations of the peaks of the the aurora. We have adopted, at least initially, just a very simple separable covariance function, partly because it's easy. It's computationally easy. I think Jonty's going to probably tell us it doesn't work, but we'll get to it, right? But at least right off the bat, computationally, this was the easiest thing we could think about doing. We do use a Matern. Smoothness of 2 gives us enough smoothness to try to capture what we're trying to capture, but we don't, gives us also some computational benefits as well. We also build in a cross covariance between energy and flux. This is one of Will's primary research areas, is multivariate spatial temporal covariance function generation. I'm not going to say much about it, but we are trying to tie these things together. The Gaussian processes that we're using for these coefficients are bivariate, and we're trying to tie them together in a reasonable way. We'd love to throw all this stuff into a big Bayesian computation. Right now that doesn't make a lot of sense computationally. We're doing kind of an empirical Bayes approach, I guess. In other words, maybe we're cheating. We simply estimate the parameters offline and then plug these in and use simply Metropolis Hastings to go after the calibration parameters by themselves. So some results here for energy. The values of this probably doesn't mean anything to you guys, but for energy seems to be driven mostly by that alpha parameter. Works pretty well. Beta, R. We seem to be getting some reasonable posterior distributions. We could probably tighten them up a little bit since they're pushing up against boundaries. For flux is not really a strong function of alpha, so when we run it by flux by itself, we see alpha gets more diffuse. It's more driven by beta and R. And when we try to do energy and flux together, we actually get kind of it doesn't really know what's going on. We get kind of some bimodality on beta, which is sort of consistent with Matt's work, although Matt, I think you got bimodality with R, right? Yeah, so there's kind of something going on here. I have a few comments here at the end and kind of can talk about it. So I'm winding down here. Conclusions. That's not really what I want to talk about. Oops, right? So somewhere about a little over a month ago, we were talking to the scientists, and they're looking at what we had done, and they were wondering why we ran the experiment from 0 to 5 for alpha. Turned out it was from 0 to 0.5, not 0 to 5. So somewhere in our communications, we got screwed up, right? And I actually went back and looked at the emails, and it wasn't our fault. I'm not going to I know who it was, and I'm not going to throw him under the bus, but somewhere the communication didn't quite work. Yeah, it was you. It wasn't me, was it? No, well, Well, Shane's not here. We'll just blame Shane, right? Anyway, right? So we always got some weird results, and we thought maybe this was the problem. So we just reran the whole thing. We burned up another month of BYU's cluster, which made Shane really happy. But we still are kind of not doing something well here. We like the statistical model that we put forth for kind of, I don't really want to say emulating the model output, but in some sense that's kind of what this principal component decomposition we're doing. We've done some cross-validation like studies, and we like how we reproduce things. The problem is when we kind of add data into the mix, we get things that posteriors that push way outside any physical boundaries, or at least any boundaries that these guys think are meaningful. That's a bit of a problem, right? And we're still trying to figure it out. In part, I think, we just don't have enough information. 25 runs doesn't seem like a lot. And so, we are looking at doing some sequential design runs with the expected improvement, but I also think we got to kind of clean up the statistical model and how single and double and work with itself. And I don't know, maybe you guys can tell me, but it's not clear to me how to do the expected improvement when I have two different simulators, basically, and how to put everything together. But I think the real problem is this mix model. The actual model that gives us the precipitating electrons is just not very good. Turns out we have a new model that has 9 parameters, which doesn't seem like a lot, but they think it does a much better job of capturing things. So this is long ongoing. I do want to say, well, All right, so where are we going? Sequential design. This is just one storm. There's another scientific question, are all the storms the same? So it'd be nice to have multiple storms and either kind of think of them as multiple, multiple realizations, or maybe look at some robustness across different storms. I also would like to do something else, different kind of linkage here between the single and the double runs that maybe exploits this idea that the single is only giving us fog, the double's giving us rain, so maybe we can kind of think of as a single as maybe some sort of smooth process that's consistent with the double. So maybe that's some sort of process convolution type idea. So maybe a different way of linking the different runs together. And maybe I'll quit there, right? NCAR is a great place to visit. Anybody wants to come, we have a lot of different mechanisms for bringing people out. Anyway, thank you very much.
Questions?
All right.
Wow.
All right, one.
So what changed between the model I looked at and the mixed model? Because it's still 3 parameters.
Yeah, I know, but that's a good question. I think they changed the solver for the most part. But we reran, we did the exact same design that you ran or you worked with ages ago, and the mod, they're not the same. I mean, the same design points, but very different output. Yeah. These guys are changing this faster than we can do anything.
Yeah. I was wondering if any work had been done in investigating the emulator and its issues, and whether or not they were related to the assumptions of separability and the covariance structure.
We haven't pushed that there very far. The biggest thing we've been concerned about is that mean function, because it is so heavily tied to these equations. Like I said, we've done some cross validation work, and we're pretty pleased with how that's come up. I think the separability is a bad idea, right? Basically, because we kind of already know that these things trade off of each other, and so that's next year's talk. Yeah.
My question might be a bit naive. So when you did this dimension reduction with the EOFs, did you explore any other dimension reduction methods and possibly provide one that gives you a little bit more of an interpretation for the relationship between the inputs and the outputs?
Yeah, it'd be nice to do something that wasn't as ad hoc as principal components, right? Right now we're willing to do just about anything, right? I mean, we kind of just want to solve the problem. We haven't looked at a ton of ideas yet. Part of the reason with going with principal components is it's something that is so ingrained in the geoscience world. I kind of agree. It's a bit, I've seen too many people do AOFs and then make all these physical claims about what they see. I mean, to me, it seems like it's a bit lucky. We have, but that's where we are, right? If you have any ideas, let me know. Okay.
Well, if there are no more questions, thanks very much too.